Good morning, students. We are going to see the 7th chapter, Dual Nature of Radiation and Matter. Now we will see the first part, Dual Nature of Radiation. Topics to be covered in this lesson are Introduction, Electron Emission and its types, Photoelectric Effect, Experimental study of photoelectric effect and its variation, laws of photoelectric effect, Einstein photoelectric explanation and its equations, properties of photons, photoelectric cell and its applications. Dual nature of light. Dual means two, which means light has both wave-like and particle-like nature. What do you mean by wave nature of light? Here, light behaves as a wave as it passes through air, vacuum and other transparent media. The phenomena explained by wave nature of light are propagation of light through vacuum, reflection of light, refraction of light, phenomena of interference, diffraction and polarization. And the second one is particle nature of light. Here, light exhibits some characteristics of particles when it being absorbed or when it is being generated in a light source. The phenomena explained by particle nature of light is photoelectric effect of light, scattering of light, emission of light and absorption of light. And the next interesting topic is electron emission. What do you mean by electron emission? The ejection of free electrons from the surface of a metal is known as electron emission. Just think of it. We know that every metal has free electrons. These electrons are free to the extent that they may transfer from one atom to another within the metal, but they cannot leave the metal surface to provide electron emission because of electrostatic attraction of positive nuclei inside the atom. However, if sufficient energy is given to the electrons, their kinetic energy increases and thus the electrons will cross over the surface barrier to leave the metal. This is nothing but electron emission. The second key term we need to understand is work function. As the name work always just as energy. Hence work function will have something to do energy. Let's understand what is the meaning of work function. As we learned, there are free electrons available with energy, atoms which can be extracted from the atom or the metal surface. But they cannot be emitted just like that. They will be emitted if and only if, which means some minimum energy is required by an electron to escape from the metal surface. That is, some external energy required by an electron to escape from the metal surface. It is known as work function. It is usually denoted by the symbol phi naught. And the unit of work function is electron volts, EV. This work function of a material depends mainly on the nature of metal and electronic configuration of metal. I just mentioned in the previous slide, EV is the unit for work function and also said that work function is a kind of energy. If work function is a kind of energy, how do we talk of the units as EV, electron volts? Actually, Whenever we are expressing energy at atomic levels, we are talking of energy in lower values. Joule is going to be a very big units measuring energy at atomic levels. Thus, the smaller unit for energy at atomic levels is electron volt, EV. Work is a form of energy can be expressed as E times V. When we express W, E times V, where E is the electronic charge, then 1 electron volt turns out to be minus 1.602 into 10 power minus 19 joule. In terms of magnitude, we ignore the negative sign. Now the value for 1 electron volt is 1.602 into 10 power minus 19 joule. This table shows that work function is different for different metals and also gives the approximate value for various metals. The important thing is the material with smaller work function is more effective in electron emission because additional energy required to release the free electrons from the metal surface is smaller. So the metal selected for electron emission should have low work function. As we learned in the beginning, what is electron emission? Here, what are the types of electron emission? There are mainly 4 types of electron emission. The first one is thermionic emission. The second one is field emission. The third one is photoelectric emission. And the last one is secondary emission. The first type is thermionic emission. In this method, the metal is heated to a sufficient temperature, about 2500 degrees Celsius, to enable the free electrons to leave the metal surface. The number of electrons emitted depends on the temperature. Higher the temperature, the greater is the emission of electrons. The ejected electrons are called thermal electrons. And the examples are cathode ray tubes, X-ray tubes, electron microscopes, etc. And the second type is field emission. In this method, a strong field, that is a high positive voltage, is applied at the metal surface, which pulls the free electrons out of the metal because of the attraction of positive field. The stronger the electric field, the greater is the electron emission. The ejected electrons are called field electrons. And the examples are field emission scanning electron microscopes, field emission display, etc. The third one is photoelectric emission. In this method, the energy of light, which has a suitable frequency, falling upon the metal surface is transferred to the free electrons within the metal to enable them to leave the surface. The greater the intensity of light beam falling on the metal surface, the greater is the photoelectric emission. The ejected electrons are called photoelectrons. And the examples are photodiodes, photoelectric cells, etc. The last type of electron emission is secondary emission. In this method, a high velocity beam of primary electrons strikes the metal surface. The intensity of secondary emission depends upon the emitter material, mass, and energy of bombarding particles. The ejected electrons are called secondary electrons. Examples: image intensifiers, photomultiplier tubes, etc. The most important topic is photoelectric effect. What do you mean by photoelectric effect? The phenomena of emission of electrons from a metal surface when radiations of suitable frequency is incident on it is called photoelectric effect. From the figure, when radiation of light rays which has a frequency is incident on the metal, there will be a emission of electrons. These electrons emitted by this effect are called photoelectrons, and the current constituted by photoelectrons is known as photoelectric current or photocurrent. It was discovered by Heinrich Hertz in 1887 during his electromagnetic waves experiment. And the next is threshold frequency, which denoted as nu naught. The minimum frequency of light which can eject photoelectrons from a metal surface is called threshold frequency. The next, threshold wavelength, that is lambda maximum. The maximum wavelength of light which can eject photoelectrons from a metal surface is called threshold wavelength. Now, the relationship between work function, threshold frequency and threshold wavelength is phi equal to h nu naught. And the nu naught equation is C by lambda maximum. Hence the equation is phi equal to hc by lambda maximum. Just think of it, how to understand the photoelectric effect. When a ball is hitting into a outer space, if you don't hit it hard enough, it will just come back down. No matter how many times you hit it. If Superman hit it, he could get it into space. Similarly, no matter how many photons strike the metal, if none of them has sufficient energy to eject an electron from a metal atom, you won't get a current. If the energy taken up by the electron is sufficient to allow it to be released from the metal atom, you will get a current. Experimental study of photoelectric effect. Philip Lenard studied the photoelectric effect practically. This figure shows the experimental setup. C is the metallic cathode, A is the metallic anode, W is the quartz window. When a light of suitable frequency falls on the metallic cathode, photoelectrons are emitted. These photoelectrons are attracted towards the positive anode and hence photoelectric current is constituted, and the current is measured by using microammeter. The variation of photocurrent with respect to intensity of incident light, potential difference between the electrodes and the frequency of incident light. The first variation is effect of intensity on photocurrent. Current is number of electrons passing through a cross section in unit time. As the intensity increases, correspondingly number of electrons emitted is also increases and the current is increased. Hence it implies that photocurrent is proportional to intensity. Here a graph is drawn between light intensity along x-axis and the photocurrent along y-axis. From the graph, the photocurrent, the number of electrons emitted per second, is directly proportional to the intensity of the incident light. Effect of collector potential. Collector potential is meant for collecting emitted electrons. Current first increases with increase in collector potential, after which it saturates. It saturates when emitted electrons is equal to the collected electrons. This maximum current is called saturated current. Now we keep voltage negative, it will repel electrons. At some potential, all electrons will get repelled. At this potential, photocurrent will be zero. This is called stopping potential. So the maximum kinetic energy is equal to the work done by the stopping potential, that is EV naught. So the equation is kinetic energy maximum is equal to half mv square maximum is equal to EV naught. By doing cross multiplication, V maximum equal to root of 2 EV naught by m. By substituting the known values of the equation, we get that V maximum is equal to root of 2 into 1.602 into 10 power minus 19 by 9.1 into 10 power minus 31 into V naught. Now the value is 5.93 into 10 power 5 into root of V naught. Hence kinetic energy maximum is equal to EV naught in terms of joule. In electron volt, kinetic energy maximum is equal to V naught. From the graph, when the intensity of incident light alone is increased, the saturation current is also increases, but the value of V naught remains constant. From this, we can say that the maximum kinetic energy of the photoelectrons is independent of intensity of the incident light. The third variation is effect of frequency. For fixed intensity of incident light, the photoelectric current does not depend on the frequency of incident light. At that time, saturation current will be same for all frequencies is greater than the threshold frequencies. The graph between frequency and stopping potential is always a straight line and implies that there is always a minimum frequency below which there is no photocurrent. That frequency is called threshold frequency. Here the graph is drawn between frequency and the stopping potential for different metals. It is found that stopping potential varies linearly with the frequency. Below a certain frequency called threshold frequency, no electrons are emitted, hence stopping potential is zero. Now the very important topic is laws of photoelectric effect. The first point is, for a given frequency of incident light, the number of photoelectrons emitted is directly proportional to the intensity of incident light. The second point is, maximum kinetic energy of the photoelectrons is independent of intensity of the incident light. The third one is, maximum kinetic energy of the photoelectrons from a given metal is directly proportional to the frequency of incident light. For a given surface, the emission of photoelectrons takes place only if the frequency of incident light is greater than a certain minimum frequency called the threshold frequency. The last one is, there is no time lag between incidence of light and ejection of photoelectrons. Einstein photoelectric explanation. According to Planck's quantum theory, light is emitted from a source in the forms of bundles of energy called photons. Energy of each photon is E equal to h nu, where h is a Planck constant and the value is 6.626 into 10 power minus 34 joule second. Einstein made use of this theory to explain how photoelectric emission takes place. According to him, when photons of energy fall on a metal surface, they transfer their energy to the electrons of metal. A quantum of light has linear momentum, and the magnitude of that linear momentum is P equal to h nu by c, where c is the speed of light in air. The individual light quantum of definite energy and momentum can be associated with a particle. Now we will see the properties of photons. A photon travels at a speed of light c in vacuum, that is 3 into 10 power 8 meter per second. It has zero rest mass, that is, the photon cannot exist at rest. The kinetic mass of photon is m equal to E by c square, that is equal to h by c lambda. The momentum of photon is P equal to E by c, that is equal to h by lambda. Photons travels in a straight line. Energy of a photon depends upon frequency of the photon, so the energy of photon does not change when photon travels from one medium to another. Wavelength of the photon changes in different media, so velocity of a photon is different in different media. Photons are electrically neutral. Photons may show diffraction under given conditions. Photons are not deviated by magnetic and electric field. Einstein photoelectric equation. When a photon of energy h nu falls on a metal surface, the energy of the photon is absorbed by the electron and is used in two ways. The one is, a part of energy is used to overcome the surface barrier and come out of the metal surface. This part of the energy is called work function, that is phi equal to h nu naught. The remaining part of the energy is kinetic energy of the photoelectrons, that is half mv square, where m is the mass of the photoelectron and v is the velocity. According to law of conservation of energy, the energy equal to work function plus kinetic energy. Hence, h nu equal to phi plus half mv square. If we reduce the frequency, kinetic energy is also reduced. Then nu equal to nu naught and kinetic energy becomes 0. Then the equation becomes h nu naught equal to phi naught. Substitute the second equation in equation 1, then we get h nu equal to h nu naught plus half mv square. This equation is known as Einstein's photoelectric equation. If the electron does not lose energy, then kinetic energy is maximum. At the time the equation, kinetic energy maximum is equal to h nu minus phi naught. From this, A graph is between maximum kinetic energy of the photoelectron and frequency of the incident light is a straight line. By Einstein equation was experimentally verified by Millikan. So he drew a graph between the maximum kinetic energy versus frequency for many metals like potassium, sodium, zinc, platinum, etc. It is found that the slope is independent of the metals. By the conclusion of Einstein's explanation, the maximum kinetic energy is proportional to the frequency of the light and is independent of the intensity of incident light. The most interesting topic is photoelectric cell. Photoelectric cell is a device which converts light energy into electrical energy. It works on the principle of photoelectric effect. It is broadly classified into three types. The one is photoemissive cell, photovoltaic cell, and photoconductive cell. What is photoemissive cell? Its workings depends on the electron emission from a metal cathode due to irradiation of light. Photovoltaic cell. A sensitive element made of semiconductor is used which generates voltage proportional to the intensity of light. Photoconductive cell. The resistance of the semiconductor changes in accordance with the radiant energy incident on it. The brief explanation of photoemissive cell. It is a device which converts light energy into electrical energy. It is also called as photocell or electric eye. It consists of quartz bulb in which two electrodes. The one is cathode and the one is anode. Cathode is nothing but negative electrode. Anode is a positive electrode. Here, a potential difference is applied between the anode and the cathode through a galvanometer G. When the radiation of suitable frequency is made to fall on a cathode, photoelectrons are emitted, which are attracted by the anode. Anode is kept at positive potential with respect to cathode. This arrangement results in the flow of current when the radiation falls on the metal surface. This current can be measured using the galvanometer. Here are some of the applications of photocells. Photoelectric cells are used in the television camera for telecasting scenes and also used in the phototelegraphy. Photocells are used for sound recording and video recording. It is used in burglar alarms and fire alarms. Photocells are used to measure the temperature of stars and study their spectrum. They are used for the determination of the Planck constant. In paper industry, to measure the thickness of paper. It is also used in automatic switching of street lights, which means without any manual attention. In beauty meter to measure the fair complexion of skin. Light meters used in cinema industry to check the light. And these photocells are used to locate the flaws or holes in the finished goods. With this, the first part is over. We just recollect what are the topics we had seen. Electron emission and its types, photoelectric effect, experimental study of photoelectric effect and its variations, laws of photoelectric effect,
Einstein's photoelectric equations and its explanations, and characteristics of photons and photocells and its applications. Thank you.